Well, thank you very much, and I want to thank Fabio and the organizers of this meeting for inviting me. For inviting me to address such a distinctive audience, and I'm really pleased to do it. And listen, I usually don't like to read things because I find it terribly boring. But anyway, I want to be sure that I said precisely what I meant to say, so I'm going to read. And don't worry, it's not too long. In fact, it's very short. And I make the best so you can follow my reading. Well, when Fabio asked me what I would like to talk about, I asked him what is the colloquium going to be about, and he said exactness, certainty. I thought, okay, I talk about exactness, okay, and exactness in the exacted sciences. And why that? Because I think I take physics has a paradigm of empirical science that is exact, and it is exact to the extent of its use of mathematics, and in many ways. I detected three different ways in which mathematics comes into physics. And the reason I chose this topic is because I am particularly interested in the role of mathematics plays in science from a philosophical perspective. It's purely philosophical, okay? It's not logical, it's not scientific in any way, it's purely philosophical. And as I see it, you know, being philosophical, it has to ask very basic elementary questions that scientists maybe find not interesting, but which I find exciting. So I go on, I'll start my reading, and if there is anything that anyone cannot understand, please tell me and I repeat. Okay, there is an obvious sense in which a science is exact if it is a system of irrefutable apodictic truth. Unfortunately, so conceived the notion of exactness, no science, not even logic, is exact. For no science exists that does not rest on removable grounds, grounds that can just go away, not even logic. Well, I think logic rests on presuppositions of ontological, epistemological, and transcendental nature, which, if not hypotheses in the ordinary sense, are not irrefragable as the existence of many different systems of logic show. We can weaken this requirement by asking only that exacted sciences should draw necessary conclusions from established foundations, themselves may be only hypothetically or axiomatically valid. Now, in this sense, both logic and mathematics qualify, for both rest on assertions that explicate how certain concepts are understood, those of truth, space, number, for instance, with everything else following necessarily from that. Purely formal mathematics, although not involving the notion of truth, does involve that of conditional truth. So, this would of course exclude every other science, particularly the empirical sciences, whose ultimate foundation, the testimony of the senses, is irremediably fallible, always revisable, and incapable of determining on lines of pure necessity all the assertions the sciences take for established. Is there a sense in which at least some empirical sciences can be properly called exact? Physics is often so called. Is there any substance in this appellation? If there is one, it has to do with the role mathematics plays in physics. And I want here precisely to offer some views on what role I think this may be. I recognize the three distinct but interdependent uses of mathematics in physics, which I call descriptive, predictive, and heuristic. The first, descriptive, has to do with the mathematical modeling of reality, both experienced reality and transcendent reality. The second, predictive, with the use of mathematics for predetermining the outcome of experience. The third, heuristic, with using mathematics even when there is no justifiable reason for so doing as an instrument of empirical discovery, although this must be taken with at least a grain of salt. To make my ideas clear, let me consider a paradigmatic case whose fundamental status cannot be questioned: physical geometry, that is, the mathematical theory of physical space. The first thing to be noted is that physical space is not simply space as detected by the senses. Distinctions must be made. There is first sensorial space, or better, sensorial spaces in the plural, related to different sensorial systems, visual, tactile, kinesthetic, which coalesce by the action of innate psychophysical functions in a coherent representation of a single perceptual space, which, strictly speaking, is not simply sensorial, but a higher level representation founded on sensorial impressions, a representation that is not yet at level of understanding or reason, but is still at level of perception. The perceiving subject is actively involved in the genesis of perceptual space. He is not simply a passive receptacle where the senses imprint a representation of space. Perceptual space contains aspects that are out of reach of normally functioning sensorial systems. For example, it is represented as unbounded or even infinite and continuous, although the senses cannot reach into the global and infinitesimally local properties of space. Perceptual space is represented as homogeneous and isotropic, although there are obviously privileged positions and directions in space as sensed. The representation of perceptual space, however, abstracts from what may cause the sensation of space, non-homogeneity, and anisotropy. Devoid of content, perceptual space is pure nothingness, and since no position or direction can be privileged in the nothingness empty perceptual space is, it is represented as in itself homogeneous and isotropic. Perceptual space, then, is constituted out of sensorial space, but is not reducible to it. However, perceptual space is not yet a mathematical realm, properly speaking. It does not admit the exact determinations of mathematics. Bodies in perceptual space are not geometrical bodies, and the relations among bodies in perceptual space are not amenable to exact determinations. They may be close, the bodies may be close or far from one another, closer or further as comparable to other bodies, but not at precisely this or that distance measured by a number. Although not a mathematical structure, perceptual space has nonetheless a structure, which, however, can be better expressed by means of mereological instead of exact concepts. Mereological concepts are inexact, somehow imprecise. There are regions in perceptual space, but not points or sets of points, trajectories, but not lines, and so on. A theory of perceptual space, if we wanted to develop one, would not be exact, an exact theory, and physicists, at least those from the 17th century on, would not be interested in it. And this is worth noting. We may want to develop a theory that's by its very essence non-mathematical. Psychologists, for instance, or phenomenologists are certainly interested in a theory of perception that is essentially descriptive and non-mathematical. And here I give an example of one I like very much. It's Merleau-Ponty, Phenomenologie de la Perception. In order to become an object of mathematics, in order to become physical space, perceptual space must be reduced to its abstracted form and idealized, that is, exactified. No longer a continuous medium that can be filled with perceptual content, but a manifold of null points where geometrical figures can be drawn and precise determinations carried out. Whereas perceptual space is a continuous medium, mathematical space is not, but made instead of ideal points without extension. Whereas perceptual space is inhabited by physical bodies, physical space only contains perfectly geometrical bodies. Whereas perceptual space only admits mereological description, physical space admits exact determinations. It has already been claimed that physical space was invented by Descartes. There is enough truth in this claim, for it was Descartes who, by reducing matter to geometric extension, first conceived of a purified mathematical space as a physical entity. The exactification of physics began there and then, with Descartes and those of same orientations like Galileo. Mathematics could not have been brought from the supralunar heavens, inhabited by perfect celestial bodies and filled with the subtlest of substances, down to the infralunar sphere of a reptilian flux where we live and die, if this domain too had not been exactified. Modern exact science began by bringing to earth the perfection of the heavens. Edmund Husserl, in his last published book called The Crisis of European Sciences and Transcendental Phenomenology, published in 1936, points out to something quite remarkable concerning the mathematization of physics. Instead of a mathematical model of space devised for methodological reasons, he observes, physical space was taken by the creators of mathematical physics as the true space, that in which we effectively live, and perceptual space only has an imperfect approximation to it. By so doing, Descartes, Galileo, and others have forever put empirical reality out of reach of adequate experiencing. Platonic and Neoplatonic allegiances have certainly played a role in the reversal of ontological priorities and the obliteration of intentional constitution acts that went together with the mathematization of empirical nature that was required in order to make physics an exact science. Physical space is pure form, and as such, it has a mathematical structure. I will pass over in silence on how it acquired one, and how much of it is imported from perceptual space. A substantial amount, I say, but not all. The important thing to be remarked is that physical space is a mathematical manifold, and as such, it admits a mathematical theory, geometry in this case. To the extent that physical space is generated from perceptual space, it arguably has a Euclidean structure, since perceptual space is quasi-Euclidean. However, according to modern physics, the geometrical structure of physical space depends on its content, admitting different geometrical structures depending on the distribution of matter and energy in space. Form then depends on content. But, be as it may, physical space is taken to be a Riemannian manifold. Since the dawn of modern physics, scientists have diverged on what its particular metric may be, if it was intrinsic to space, somehow required on a priori grounds, or determined by the matter-energy tensor. They, however, never questioned that physical space was a mathematical manifold. The difference between a theory of perceptual space and a theory of physical space is the same as that between, for example, respectively, Goethe's theory of color and one developed in the context of Maxwell electromagnetism. The former has to do with sensations and perceptions, the latter only with formulas and numbers. In modern science, in the words of James Jeans in a book called Physics and Philosophy, one may dig, one may sow, one may reap, but the final harvest will always be a sheaf of mathematical formula. Perception has nothing definitive to say in the theory of physical space. On the contrary, it is mathematical reasoning that predetermines the ideal to which actual perception of physical space can only aim without ever reaching. Exactification allows the introduction of concepts that can only be defined mathematically. A simple example is that of instant or punctual velocity. Since perceptual space is not made of points, it does not make sense to talk about the velocity of a body at a determinate point of its trajectory or a determinate instant in its displacement. The concept requires a space and time made of points and instants, and it can only be properly defined mathematically. Another good example is that of entropy, a thermodynamic concept that requires an already well-developed mathematization of the realm of thermal phenomena, even if we remain on the macroscopic level of description. Although the emergence of physical space is a good example of the process of exactification of natural realms, it's not paradigmatic of all instances of this process. The idealization that brought about physical space had perceptual space to act upon, which had already a robust structure. But there are realms of reality perception can only touch, and even though by the intermediation of sophisticated instruments. In this case, perception can at best provide a mass of data corresponding to certain choices we make, choices that privilege the mathematically expressible, and data which are already idealizations of what we can actually perceive. With no clue on the subjacent structure, scientists can rely only on regularities they manage to discern in the available data and guess, to the best of their talents, what might be behind these regularities in the ideal mathematical realm they take transcendent empirical reality to be, with no guarantee that there is indeed a transcendently real subjacent structure, for we may see things that do not exist objectively, or that the one they come up with is the real article. Guesswork often rely on similarities between perceivable regularities in different domains of experience. An interesting example of this scientific strategy is Maxwell's discovery, quotation marks, of displacement current and consequently electromagnetic waves. Due to observable formal similarities between the mechanical and electromagnetic domains of observable phenomena, Maxwell conceived a very ingenious mechanism, in the literal sense of the word, consisting of vortices and strings in an elastic medium to account for electromagnetic phenomena. By using this mechanism to explain the storage of energy in dielectrics, he came up with the concept of displacement current, which could also be used to restore consistency in the system of equations he inherited from Ampere, Faraday, and others, so establishing the so-called Maxwell equations and making way for the discovery of electromagnetic waves by Hertz. This is a good example of the use of mathematics in science, and I call it heuristic. To reason by formal analogy requires that domains of reality be mathematized, so opening the possibility that different domains be given the same or sufficiently similar subjacent mathematical structures. The fact that a domain of empirical reality has a mathematical structure does not mean, as Eugene Wigner and Max Steiner have suggested, that nature is intrinsically and mysteriously mathematical, only that this is how we made it to be. And the apparently marvelous fact that two completely different domains of reality have equal or similar mathematical structures may only indicate that we don't have data-rich stock of mathematical structures to impose on reality, either the one effectively perceived or the transcendent reality we presuppose to stand out there. The descriptive use of mathematics in physics, then, which requires the exactification of perceptual reality, opens possibilities for risky uses of mathematics in physics. Another good example of guesswork was or is the mathematization of the mass of experimental data arising in connection with the interaction between matter and radiation at the turn of 19th to the 20th century. The data alone did not display eloquent enough subjacent structure for a mathematization to stand out as the correct one, as Euclidean geometry did for the ideal structure of perceptual space. Attempts to structure the data classically did not work without ad hoc hypotheses and had eventually to be abandoned. Scientists like Rutherford, Bohr, and de Broglie resorted to imagination to concoct physical and mathematical models of reality that would explain the data, while others like Heisenberg, Born, and Dirac relied on formal analogies, skipping physical models altogether. The fact that quantum mechanics admits different but equivalent mathematical formulations testifies to the fact that different mathematical structures can fit the same chunk of reality. The mathematization of empirical reality went as far as giving physical reality to entities so obviously mathematical, such as scalar, vector, and tensor fields, so that a clear distinction between physical and mathematical realities can no longer be maintained. Fields, no longer mathematical devices to circumvent spooky action at distance, are now taken as part of physical reality. There are philosophers of mathematics who think of mathematical existence in exactly the same terms as empirical existence, and see the usefulness of mathematics in science as a sign that mathematical entities exist just like real objects, only not in physical space. But why not, if physical space is a mathematical manifold? Having reduced the empirical world to a mathematical manifold, physics could then transmute itself into mathematics, mathematical physics. The world became a mathematical object, and physics is hardly different from mathematics. Mathematics can now take upon itself the task of predetermined experience. This is what I have called the predictive role of mathematics in science. Mathematical equations now cut the path along which empirical reality must follow. Mathematics only has the right to tell how reality can be experienced and what can be experienced in it, if always only approximately, predetermining to some extent that which has by right the power of evaluating the adequacy of the mathematical theories of nature experience. Nothing that falls outside of the mathematical determinable is physically real. Husserl, in this book I mentioned before, Crisis, although recognizing the practical utility of the mathematization of empirical reality, points out to the curious fact that it is mathematics, a product of human life, that's now in charge of predetermining what can be experienced in life regarding empirical reality. Let me concentrate for a moment in the process of exactification to see what it requires, how it comes to be, and whether it can be set as an ideal for every science. Hermann Weyl, in a beautiful book called Philosophy of Mathematics and Natural Sciences, calls our attention to an important and obvious fact that most epistemologists seem to ignore, that objective knowledge is necessarily formal. Let me explain. The material content of our perceptions is irremediably private. The experiences of hearing a sound, tasting pomegranate, touching silk, or feeling the flow of time are only mine. To communicate it to others, or these feelings to others, or these sensations, I must rely on language. If I'm a poet, I may use language in a peculiar, non-descriptive way in the attempt to induce in others, by analogy or resonance, sensations I deem analogous to those I myself experience. But if I am a scientist, I must faithfully describe, or try to. By describing my perceptual experiences, however, all I can express are their formal aspects, which completely different experiences can also display. Let me prove this. No matter how appropriate a language is to express my perceptions and how successful I am in describing them, the result is invariably a collection of assertions that can be reinterpreted in a completely different context salva veritate. That is, the hyletic content of perception escapes description and only its form is captured by it. In other words, reference cannot be fixed descriptively. Hence, only the formal abstract aspects of experiences can be linguistically objectified. And since the object of empirical science is objective, experienceable reality, empirical science can express only the formal aspects, abstract formal aspects of reality. So, all sciences are formal, but some sciences are also exact. Exactness is achieved by privileging the language and conceptual apparatus of mathematics for expressing the formal abstract aspects of reality. Now, how desirable exactness is. Not all sciences can afford it. We can afford exactness. Are they then falling short of an ideal? Exactness has a price, which physics at some moment of its history decided to pay. By declaring that the book of nature was written in geometrical characters, Galileo was not stating a fact. He was making a decision. If we pay attention to his words, he was not saying that nature was intrinsically mathematical, but only that this is how we can read it, how it can be described. By becoming exact, physics became something it was not before the scientific revolution of the 17th century, namely, the science of convenient mathematical substitutes of empirical reality. Other sciences may decline exactification for basically two reasons. The perceptually given may be regarded as a permanent source of information. The scientist may have to constantly consult perception for extracting formal structure from it. Or she may be interested exclusively on what mathematical exactification leaves behind. Any aspect of reality that does not fit into mathematical garb is deemed, from the perspective of the mathematical sciences of nature, a scientifically irrelevant aspect of reality. One of the most resilient naivete of the practitioner scientists is to take what the process of exactification must necessarily let go, not simply as irrelevant from the perspective of the exact sciences, but as scientifically irrelevant to who? And concepts that cannot and need not be exact as poorly defined concepts. But it may be the case that the experiences we want to capture conceptually and describe are by their very essence incapable of being faithfully represented mathematically. And we don't have to go to psychology to find an example. The experience of continuity will do. In mathematical theory of the continuum, as Hermann tells us in another beautiful book of 1918 called the Das Continuum, so he says, any mathematical theory of the continuum falsifies it. The continuum of perception is not atomized, but the mathematical continuum, geometrical or arithmetical, are. The flow of time as you experience it is not a continuum. But this is how mathematics can express it, and this is the only way mathematics can express it, by marking points in it. The flow of time as you experience it is not a set of instants jammed together without gaps, but mathematics cannot represent it otherwise. According to Weyer, the exact rendition of intuitive continuum in mathematical terms can only be justified by the scientific requisite of preserving from intuition only what can be objectified, which, as I have shown, are their formal aspects. And and by the fact that expressing the formal content of intuition in exact mathematical concepts and language allows us to resort to the rich stock of mathematical sciences, in themselves nothing but formal descriptions of possible formal realms. But he was very clear about this. The adequacy of such a decision had to show its value in practice. So, and I conclude, exactness is not a value in itself, which every science should cherish. It certainly could be useful, but, as Husserl observed in Crisis, at the risk of alienating man from the world where he lives and actually experiences, giving mathematics the power to describe reality, to prescribe what we can experience in reality, and to guess how reality may be, is a method, besides expressing an ideal, that of the infinite refinement of experience, and as any method, it cannot claim universal adequacy. Thank you.